All right. So let me paste this down here. And we're going to start with this first. And let me do this real quick. I sent you this already. I sent you a copy of, well, a link to this document containing polyatomics. So we're going to need that. Now this, you definitely are going to have to commit to memory because a lot of these polyatomics are going to show up multiple times throughout the semester. So you need to be familiar with them. So for the first problem that we're going to work through, and I'm gonna talk about like a lot of different facets of these problems. So this example right here may take us the whole time. I know it did this morning. All right, so the document that I just put in the chat, go ahead and open that up. And those of you who are once you have it open, I want you to look up this polyatomic right here. This is what we call a polyatomic anion. All right, so it's an anion composed of multiple atoms. All right, so it's composed of multiple atoms. That's why we call it a poly, meaning many, atomic. So polyatomic. Anybody found it on the document yet? Feel free to scroll down. It's actually it's in the second group on the first page. Put it in brackets. Anybody got it yet? Can't see. I have to upload. Or if you're on your phone, Lauren, it's not going to show up. But you can get it from Blackboard. If you can get the Blackboard and open the link, you can get it from there. But I'll upload it again. All right. Nobody found it, huh? So this is the perchlorate ion. All right. If you look on that document that I uploaded, it's in the second group of polyatomics near the bottom. And there are multiple polyatomics that have chlorine and oxygen in them. So the perchlorate is one, and then chlorate, and then chlorite. So perchlorate, we haven't talked about Lewis structures yet, but let me show you what that looks like. So there's a chlorine in the middle, and it has a double bond to oxygen, two double bonds to oxygen actually. And then two single bonds to oxygen. And these oxygens have lone pairs. We're going to talk about this when we start talking about Lewis structures. But the electrons around oxygen give it a formal charge. Give the oxygens that have single bonds a formal charge of -1. And then chlorine itself has a charge of +1. All right. So overall, the perchlorate anion has a overall charge of -1 because the two oxygen charges add up to -2, and then the chlorine is +1. All right. Any questions about that? All right. So that's the perchlorate anion. And the question asked for each of the following compounds, state whether it is ionic or covalent. And if it's ionic, write the symbols for the ions involved. So we're going to do that too, because that's going to help us to understand the crisscross method that I showed you before with the charges and things like that. All right. So in order for a compound to be ionic, that's going to happen when you have a metal plus a non-metal. Right, that's going to give you an ionic compound. All right, and most of 99% of your metals, really all metals are cationic, but there are some instances where a metal can be negative, but it doesn't exist by itself in a negative state. It usually has some other substituents attached to it that cause it to be negative, but 99.999%, the metal is the cation. So it has a plus charge. And then non-metals, 99.999% are going to be the anion in a compound like the ones we're looking at here. Right, it has a negative charge. That's a term that we've already learned. Right, so if it's ionic, normally it's going to be a metal and a non-metal. If it is covalent, that's generally going to be between two non-metals. Right. So can somebody tell me what the difference is in ionic and covalent? Anybody remember that? Right. So a covalent bond is a bond between two atoms where they share a pair of electrons. An ionic bond is really not a bond, right? This is simply an electrostatic attraction. Something positive being attracted to something negative. Right. So if something is ionic, that's going to be a fully positive part and a fully negative part. If it's covalent, there's going to be a shared pair of electrons. All right. Now that a covalent bond can be polarized. We'll talk about that later. But for this example, for the potassium perchlorate, what do you think? Is that ionic or covalent? All right. All right. Think about it this way. Is potassium a metal or a non-metal? Look at your periodic table and tell me if potassium is a metal or non-metal. And how do we know if it's a metal or a non-metal? What feature of the periodic table gives that away? All right, let me see. Somebody put it in the chat. Okay, I agree. Metal. I was about to call you metal, Mary. I agree. Potassium is a metal. It's in group 1. Anything to the right of that zigzag line. Remember the line we showed where the metalloids are, boron and aluminum is a late transition metal, but it's on the other side of the zigzag. So anything on the other side, on the left side of that zigzag, on the periodic table is a metal, right? So yes, potassium is a metal. It's a alkali metal. This is metal plus the perchlorate anion. Both chlorine and oxygen are non-metal, so this is a metal plus a non-metal. Right. So this compound is ionic. Now let's think about this. If the perchlorate has a -1 charge and potassium is a group 1 atom and a group one element and a metal, if you remember these subscripts down here, even though I don't have them shown, are understood to be 1. All right. So the way we can figure out like the pieces or the ions in that compound is to think about it like um, pulling Play-Doh apart, right? So we have a piece of Play-Doh in the middle and holding it with both hands. If we pull it apart, then we're pulling the components of the compound apart also. When that happens, this number down here is going to end up here, right, as the charge. And then this number right here is going to end up, let me change the color on that. This number here is going to end up here as the charge, right? So when we pull these apart into the components, the subscripts become the charges. And I'll explain that right? So when we pull those two atoms apart, the one that's down on the right, that's circled in pink, is going to be the charge for potassium, which is going to be what? Anybody, unmute and speak up. When I pull the potassium away from the perchlorate, what number is going to be a superscript for potassium as the charge? We know it's going to be positive because metals have positive charges. All right, so this is going to be K plus 1. And then the perchlorate, I'm going to leave it in brackets, ClO4, it's going to be -1. Right? So if I have the names and I know the charges, then when I put them together, the opposite happens, right? So when I crisscross these over, this one goes here and this one goes here. When I pull them apart, the subscripts go back to being superscripts, right? We're going to do another one so this will make more sense. So these are the ions that came together to make this compound. K plus, potassium plus 1, and the perchlorate anion. All right, any questions about that? Don't let this go over your head because you're going to see this a lot. You can't get away from it. This is going to be like a part of our regular routine, knowing the names of these compounds and things like that. So don't let it go over your head. All right, let's do the next one. Let's take and here's the thing about why this happens like this. If the molecule itself, the compound itself, is neutral, then that means that the charges have to cancel each other, right? So since K is +1 and perchlorate is -1, it only takes one perchlorate anion to satisfy one potassium cation, right? In the next example, that's going to be different. So let's look at the next example, which is magnesium. I keep giving it away. I don't want to say the name because I want you to name it yourself. So it's Mg, and it is C2H3O2. and there's a 2 subscripted out here. What does that 2 mean? It means that there are 2 of these ions. So 2 of those anions. All right. So in this particular case, this is again a metal. Magnesium is a metal. And then this is a non-metal. All right. So in this particular case, is this ionic or covalent? Help me out. Remember, if the compound is ionic, it's going to be a metal and a non-metal. If it's covalent, it's going to be 2 non-metals. Yeah, it is. Thank you, Mary. It is ionic. It is ionic. So now, since we know that it's ionic, let's get the components and see what they look like. So we have to pull them apart. So we're going to grab the magnesium and we're going to grab this other ion and pull them away from one another. What's going to happen? So, you know, this is understood to be 1. I didn't write it because it's understood to be 1. And then this is 2. So when I pull them apart, the 2 is going to end up coming here, right? And the 1 is going to end up coming, not like that, sorry, here as a superscript, right? So we're going to get what? Mg, what's the charge on it? If the 2 comes up as the charge, go ahead.
Is it 2?
2 plus, yes. If it's a metal, it's going to have a positive charge. So we always make sure we indicate that it's 2 plus or plus 2. And then what about the anion? So that right now we know that that's that the metal is the cation. So the other piece of the compound by default has to be the anion. So this is C2H3O2. What's the charge on that? Remember, this is understood down here to be 1. All right. So the charge on that has to be -1. Those are the 2 pieces that came together. Can you see now why the 2 is down here in the subscript for that anion? Because magnesium has a charge of +2. You need 2 of those anions to satisfy it, right? To make it neutral. And so that's why that subscript is down there. So you got to have 2 anions to satisfy the 2 plus charge on magnesium. Both anions are -1. And so that's going to take that +2 charge down to 0. All right, we got to name it now. So I already gave away the metal, which is magnesium. Can somebody look on the sheet that I uploaded to the chat and tell me what this ion is, what this polyatomic is, because this is also a polyatomic. It's going to be, let's see, the second page, and it's going to be the first list on the second page. Let's see, I got 3 people in the chat. Okay, good. Acetate. Excellent. Thanks, Mary. So that is the acetate ion, right? You might have heard this before. The acetate ion is basically how do I put this without going over too far over into another topic? It's a derivative of acetic acid, which is the principal component in vinegar, right? So let me show you what that looks like. So the C2 part is here. So this is CH3, C, that's so here are my 2 carbons. And then here's my 3 hydrogens. And then that carbon in the middle has a double bond to oxygen, O, and then single bond to oxygen, O, like that. And that oxygen is negative. All right, so this is the acetate anion. That's why you see it sometimes written like it is on that sheet, CH3COO minus. That's an abbreviation for it. Or you can see it written how we have it, C2H3O2. All right. Now we had talked about something prior to this with formal charge. And I gave you a kind of rudimentary way to calculate that. Does anybody remember when we talked about formal charge? Let's see if we can kind of jog our memories and go back and figure out why oxygen is negative here. Anybody remember that little formula I gave you for calculating that? If not, it's okay.
I think it was the valence electrons versus minus the actual electrons.
God, I mean, I meant that in a good way. Who was that?
Anya?
Nice work. Nice work. That's exactly right. It's the valence minus actual. I think you just earned lunch today. That's great. All right. So valence for oxygen, if you look on the periodic table, oxygen is in group 6. So the valence electrons would be equal to 6. All right, and this is for oxygen. All right, so valence is 6, and then actual is, you have 3 lone pairs, 1, 2, 3. So that's 6 electrons, and then that covalent bond right here is actually a shared pair of electrons between carbon and oxygen. So I'm gonna write that in like this. So here, even though they're unevenly shared closer to oxygen, they're shared, right? So actual will be half of whatever the bond is. So if the bond has 2 electrons in it, then the actual is going to be 1. So the total number of electrons around oxygen right there is the 3 lone pairs, that's 6, and 1 from the bond, so that's 7. So 6 minus 7 is -1. So that's why oxygen has a negative charge. And we're going to do a lot of that. I just slid that in because there's a good opportunity. We're going to do a lot more of this as we progress, and you're going to see all these little topics that keep popping up. And I'll tell you, like, I'll just keep it a bean with you. If you learn these little fundamental things, when you get to your higher level classes, they're going to be so much easier. So take the time to learn this stuff now. Don't breeze through it. Don't sleep through it. Don't sleepwalk through it. Grab it, hold on to it, ingest it, all of that. Because I promise you, you're going to see all of this stuff again, more over and over and over. Every chemistry class you take, you're going to see these same concepts keep cropping up. All right. So that's how we get a -1 charge there. But that's besides the point. So I just wanted to throw that in. So the acetate is a polyatomic. It has a -1 charge. And when you memorizing your polyatomics, always memorize the charges, because the charges make up, the charges indicate the stoichiometry, right? If you don't know the charge, when you just put these 2 things together, then the compound is not going to have the right ratio of elements. So you got to know the charges and the actual polyatomic ion itself. All right. So let's go to the next one. Actually, I want to do them all of ionic ones first, and then we'll come back and finish up the covalent one. So let's go to let's do D, and then we'll come back and do C and E together, because both of those are covalent. So let's do D, which is Ag2S. Now, I need somebody to tell me what the symbol for Ag means. What's that symbol for? And for S. And if it's, well, I kind of gave it away that it's ionic, but which one is the metal? Which one is the non-metal?
I'm sorry, what was
AG is silver.
Silver. Okay, good. So this is silver. What about sulfur?
You just said it.
Oh. Thank you for catching me on that. And this is sulfur. All right. Now it's ionic. What do the two pieces look like if we pull these two things apart? What's the subscript here understood to be?
One.
One. Good. So if we pull them apart, what's the charge going to be on silver, and what would the charge be on sulfur? Think about like a piece of Play-Doh. You just pull it apart with part of it in your left hand, part of it in your right hand. You just pull them apart. And when you do that, the numbers here end up superscripted.
Do they switch?
They do switch. So the numbers end up superscripted. All right. So what would the charge be on silver?
+1.
+1. Excellent. And then on sulfur is going to be what? By
Is it
default,
-2?
yes, -2. By default, it's got to be negative if the silver is positive. All right. So now we have the silver as the cation and the sulfur as the anion, which gives us another piece of information for naming, right? When you have sulfur, if it's just by itself, it's sulfur. But if it's the anion in a compound, then we have to change the suffix. So we're going to add, instead of sulfur, we're going to drop this ending. And then we're going to make this sulfide, IDE, right? This is what we call a suffix. We add a suffix to indicate that sulfur is the negative part of that compound. So we go from sulfur to sulfide. Any of your non-metals, whatever the name is, if it's an anion, if it's negative, we change. That's the ending that we're going to use. IDE. Any of your non-metals, like just by themselves, now not as part of a polyatomic, but just by themselves. So if oxygen was by itself, right? Or if it's one, the atom oxygen, and it's in a compound with a atom like silver or gold or something like that, it's going to be oxide. If carbon was by itself as one of the atoms in here, it would be carbide, so on and so forth. So that suffix "ide," if I had chlorine, right? If this was AgCl, then that chlorine, we change the suffix to chloride. And then the suffix tells me that the chlorine has a negative charge. All right. So let's go ahead and name this compound now. So if it's Ag2S, what is it? Silver what?
Sulfide.
Sulfide. Excellent. Silver sulfide. All right. We don't worry about the numbers or any of that when we're naming ionic compounds, unless there's a specific case where we worry about the numbers. And we're going to do that. We're going to do an example like that now. All right. Any questions about this example right here? All right. Let's do another example. Let's do which one is that? F. Let's do F. And then we're going to come back to C and D, because those are both non-metals. So we'll come back to that. So it gave us, for F, CO and then NO3 with a subscript 2. Somebody look up NO3 on the chart. Tell me what it is. Anybody found it yet? It should be on that first page. Good. Thank you, Anye. It's nitrate. It's the nitrate. And is it an anion or a cation? We know the answer, but I just want to make sure we're on the same page because we already said that the metal itself is always going to be the cation in these types of compounds. So the nitrate by default is going to be what? Anion or cation? Right? It's an anion. If you look at the chart, NO3 is -1. Let me show you what that looks like. So it is a nitrogen as the central atom. And this will make a lot more sense when we start doing Lewis structures. I'm actually going to send you a video today, kind of walking you through those Lewis structures so we can, because it's something that's not hard to teach or hard to learn, but it's cumbersome. So I want to introduce you to it outside of class, so when we come back, we can just hit it. All right, so this is, somebody tell me what the formal charge on nitrogen would be. If the valence is 5 for nitrogen, what's the actual? If we take 1 electron from every bond that's on nitrogen, the double bond does count twice.
Was to be 1?
The charge?
Yeah, is it 1?
Yes.
I'm not tripping.
It's +1. That's exactly right. The actual is 4. There's 1 electron in each bond shared with nitrogen, so valence minus actual will be +1. We'll normally just write it as a plus like that. All right. So the overall charge on the nitrate anion is -1. So then when we come over here, what metal is this? It's a transition metal. I'll give you that hint. But look at the periodic table, find it in the transition metal.
You want the name?
Yes.
It's cobalt.
Cobalt. Good. All right. So now let's see the pieces, the parts of this ion. How do we do that? If we have the actual, I said ion, this compound, if we have the compound itself, how do we show the 2 ions that came together to make it, if it's an ionic compound?
Do you split them?
Split them, pull them apart. So it'd be cobalt over here and NO3. I'm gonna leave that in parentheses over here. What's the charge on cobalt? That's all.
+1.
Say that again.
Is it +1 or would it be +2?
It's always going to be this number down here, right? So it's going to be +2. Good though. You in the ballpark. This is +2. What's the charge on the nitrate again?
-1.
-1. Right? Do you see why the subscripts are important? Because the nitrate is -1, cobalt is +2. So you need 2 of those nitrates to cancel out the +2 charge on cobalt. That's why it's like that. Right? So if cobalt has a +2 charge, you need 2 things with a -1 charge to cancel it and make the whole compound neutral. All right. So cobalt with the charge here, let me slide you another piece of information. The charge here is also known as its oxidation state. All right. All that means is that That's the number of electrons that were lost. Because you know, if the charge is positive, you're losing electrons. That's the number of electrons that were lost to get to that charge. Because when something is oxidized, it loses. We haven't talked about it yet, but we'll get to it. Oxidized means you lose electrons. Reduced means you gain electrons. So cobalt can actually exist as cobalt +1 or cobalt +2. So it's got two oxidation states. Right? So when a metal has more than one oxidation, no, it's not covalent, Mary. Cobalt is still a metal, and then the NO3 is a non-metal. So it's still ionic. Good question. All right. So when a metal has more than one oxidation state, you have to indicate that in the name when you name it. So this is cobalt nitrate. But after the metal right here, you have to put in parentheses Roman numeral 2. Right? That Roman numeral 2 is indicative of the fact that this is cobalt in the 2+ oxidation state. All right, so when it's in the 2+ oxidation state, you have to indicate that. And you can tell it, right? Because you know cobalt is 2+ because of that subscript outside the nitrate, because the nitrate itself has a -1 charge. All right, what if it was cobalt 1+? How would you write that with nitrate?
Would it be Roman numeral 1, or would we just not put anything?
Well, you can put the Roman numeral, that's fine. But when we put these two together, it would just look like this, wouldn't it? It would just be CONO3 like that. And then when we write the name, it'll be cobalt 1 nitrate. Good. Any questions? All right, we got one more, I think, one more metallic compound, or is that all of them? That's all of them. Now we got to do the non-metal one. So let's do the H2S first. Right, these are both going to be covalent. Right, so both of these are covalent. And then so let's do H2S. This is actually, I was talking with the class this morning, this is actually an analog of water. Like water is H2O. Sulfur is in the same group as water, it's just one atom underneath it. And so this is an analog of water, but it's not drinkable. I wouldn't drink it. It'd be the last drink you take. So this is what we consider, this is a different class of compounds. This is considered an acid because of these hydrogens right here. So because it's an acid, we're going to write it a certain way. So we always put the hydrogens first, followed by the central atom. So the hydrogens are written first. All right, so how many hydrogens are present in this? Right, based on the stoichiometry. Good. You got the stoichiometry, the subscript, not stoichiometry, it's the same thing, but the subscript is 2 next to hydrogen. So that means that there are 2 hydrogens. And since it's covalent and 2 non-metals together, we have to write this a different way, right? Because we have to indicate the number of each atom. We don't have to do that if it's an ionic compound, but when it's a covalent compound, we do. All right. So the way that we're going to write this is to use we're going to use Greek prefixes. For the hydrogens. So di, tri, tetra, penta, so on and so forth, right? This is 2, 3, 4, 5. All right, so this will be dihydrogen. And then what about sulfur? What do you think? Do we just write dihydrogen sulfur, or do we need to put a suffix on to make sure that, you know, that we know what we're doing?
I thought you only put suffixes when there was a metal.
No, okay, so that's a good point. But when it's negative, you also have to use a suffix, because in this particular case, if we were to pull this apart, like we did the metals, even though it's covalent, we can still think of the same concept. This would be what? H plus 1, and then S minus 2. Is that right? And then if we just crisscross those charges, it will be H2S. So we know that sulfur is either negative or it has the lion's share of electrons in this compound. All right. So when we write this, it's dihydrogen
Sulfide.
sulfide. Good. We put that suffix on there because we know that the sulfur is going to, if we pull those two atoms apart, like we did the ionic compounds up top, based on those, based on the subscripts, that sulfur is going to have a -2 charge. So we write it as dihydrogen sulfide. Right. And again, the Greek prefix right here, di, means that there are two hydrogens. All right, let's do this last one and then we'll stop with that one. I think it's N2Cl4, is that right? All right, so again, these are both nonmetals. So we're going to use those prefixes. We got 2 nitrogens and we have 4 chlorines. All right. So when we write this name out, we're going to just list the atoms in the order that we see them. So this would be what? Di-nitrogen. How many chlorines do we have?
4.
So what's the prefix for 4?
Tetra.
Tetra, right? So dinitrogen, tetra, chloride, not chlorine. Right? Anytime you bond one of your halogens like chlorine, fluorine, bromine, iodine, if you bond that to another atom, the suffix automatically changes to IDE. And one thing about naming, there are so many different conventions so many different IUPAC rules, depending on what type of compound it is, if it's an acid, if it's a organic compound, if it's a ionic compound, it's like a different convention for each type of compound. So we're going to keep pushing. We got some of these other examples. We're going to stop here, but we're going to do some of the other examples on Wednesday when we come back. God willing, we'll knock out number 10 and number 9 and 10. We're gonna knock those out on Wednesday, and then we'll be Friday. I think we'll do Thursday. We'll do. I won't make another worksheet. We'll just do some practice problems, because that way you can just turn this on in once we finish it, and then Friday we'll post the exam Friday evening, and then or Friday afternoon, And then we'll still have class. We'll just be starting a new topic, but that topic will not be on exam 2. All right.